Thanks, Jake. Yeah, hi. For those of you that don't know me, my name is Kelsey York. I work for the Division of Water Quality, and I'm the MS4 coordinator. So I'm just going to give a brief introduction to stormwater. Um,
Right.
and
Right.
can can everyone hear me all right?
Yep.
Yeah, we can hear you, Kelsey. Kelsey, I think you muted yourself.
Okay,
There you go.
there we go. Okay. So, yeah, I'm Kelsey York, DWQ MS4 coordinator. I just want to do a bit of housekeeping before I got into my presentation too much. Since this webinar is not only focused, it's primarily focused to businesses and industry as opposed to cities. And in case you are not familiar with the term MS4, so MS4 means Municipal Separate Storm Sewer System. It is a term to describe both the infrastructure used within a city or county to convey stormwater runoff, as well as the owner or operator of that infrastructure. And that's kind of where I come in. So at the state of Utah, I manage a permit that cities and counties and entities like our DOT, Department of Transportation, they all have to get in order to ensure that the stormwater that's running through their system is not polluting water quality. So I manage that permit at the state of Utah. And I like to say that permit has a bunch of different users. So the city or the county or the entity is the one that manages that permit on a local level. I give them the regulations, or the state gives them the regulations. But then those users of those systems play a big role in the ultimate management of stormwater in these areas. So um, just I'm sure you'll hear the term MS4 thrown around. I just wanted to kind of introduce that term. And then the meat of my presentation will be what is stormwater, why do we care, and what are some of the common pollutants that we see in stormwater. So stormwater, I think of it as rain or snow melt that flows through cities, parks, businesses, industries, homes, pretty much anything um, that goes into the infrastructure, that MS4 system, and then is ultimately discharged to waterways, surface waters, groundwater, rivers, streams, wetlands, all that good stuff. And then I just wanted to go into a couple of different facts about it. So stormwater often discharges through infrastructure that's owned and operated by the city or county. Sometimes it's also a Department of Transportation system or a university. Um, so it often discharges through that infrastructure. It sometimes discharges through privately owned infrastructure. So that's kind of where businesses and industry come into this, where see this photo has a kind of a tree-lined swale or infiltration system in their parking lot. That's often owned by that privately owned entity, and then usually will then connect back to that city or county system. So what we would call that is there's a privately owned stormwater control in the parking lot that then discharges to the city or county infrastructure. Stormwater almost always discharges to surface water or infiltrates to groundwater. So you can see in both of the previous two photos, there's like a rock-lined ditch that's discharging potentially both to groundwater, but also being conveyed through that inlet at the end. That tree box filter is designed to infiltrate stormwater and but likely has an overflow to a public system. And then, of course, the photo here is an outlet to a stream. So that's a stormwater outlet where it discharges ultimately to the waterways. And then stormwater controls are often, if not always, designed for capacity and only sometimes designed for water quality treatment. But all all stormwater controls require regular maintenance. So you can see my photo there. There's trash chock full in this what we call a catch basin. That's the area kind of underneath a stormwater inlet, and then those two discharge pipes on the top and bottom. Those are where the stormwater fills up and then ultimately discharges or connects back to another system. So these are designed to receive a certain amount of pollutant loading, but do need to be maintained, right? Um, so sometimes they fill up with sediment. This one has been filled up with some trash. Um, so this kind of is a great segue into why do we care, right? Because and the meat of it is because stormwater often flows untreated to waterways. So this is a photo I took. I won't tell you where in Utah County, but it is in Utah County, and you can see that there's a discharge pipe to a stream. But also what you can't see in this photo is just above this discharge pipe is a stormwater inlet bed. You know, the common ones that you see just along the curb, right? So that what that shows us or what we need to know from this is that essentially water or whatever washes with that stormwater discharges through that inlet and almost immediately into this waterway. So that's why we care. Um, and I really like this graphic. It's called Stormwater, where it flows, everything goes. It's just trying to drive home the point of this infrastructure is designed to receive stormwater, and a lot of times to get stormwater out of the street quickly during the storm event and discharge it to the stream. But as we're all aware of, when it rains, pretty much anything that's in the street or in the curb and gutter or in the inlets themselves is also going to get washed down. So things like pet waste, oil and grease from cars, cigarette butts, trash, fertilizers, pesticides, car washing chemicals. As I like to say, anything that could and would mix with water that gets on pavements can become a pollutant and discharge into our waterways. With that, kind of my last section of the presentation is focused on common runoff pollutants. So probably our most common runoff pollutant is sediment. And sediment is, I know a lot of folks think like, oh, you know, there's mud in the bottom of the stream channel. Why does it matter if we're adding more mud? And that's because, of course, sediment, there's a certain amount of loading that a stream is expecting, right? And if we add more into that, that can impact wildlife. But also sediment can latch onto metals, nutrients, pretty much it's very magnetic in that way. So it can carry with it a lot of hazardous stuff, even if it just looks like dirt. Additionally, we have fertilizers, pesticides, trash, oils, fuels, grease, leaves, and organic matter. If those start to build up in the inlets, that also can really mess with the oxygen levels when they get discharged. And then illicit discharges and connections. So obviously we hope that all of our sanitary sewer is going to the sanitary sewer treatment plant to get treated, and the stormwater is the inlets are only receiving stormwater flows, but that is not always the case. So these are common stormwater pollutants and pretty much anything else that could be washed down a stormwater conveyance and mixed with stormwater to discharge. So these are just some photos of trash, debris, inlets under a dumpster, which can receive any sort of dumpster juice or trash. There's some washing, mixing with soaps. Yeah, so I guess the whole point is that really anything that could mix with stormwater and discharge would be a typical stormwater runoff pollutant. And with that, that's the end of my presentation. I think we're doing questions at the end, but I'll turn the time over to Scott.
Thanks, Kelsey. Yeah, so Scott is going to build on um, the conversation that Kelsey started with. Now we have this broad understanding of stormwater, jumping into some details about water quality conditions in Utah County specifically and how that's related to stormwater. So Scott, will turn over to you.
Thanks so much. Be able to hear me okay and see the screen?
Yep.
Perfect. Thanks so much. Well, good morning, everyone. My name is Scott Daly. I'm with the Division of Water Quality's Watershed Protection Section. I work on a variety of water quality and watershed implementation programs in Utah County, but primarily focus my attention on water quality improvement projects in Utah Lake. So today we'll talk through a little bit Utah Lake's water quality condition and how it relates to the stormwater issues that we're talking about today. Okay. Just a quick overview. Utah Lake it's more or less a focal point for water quality conditions in Utah County. It receives a lot of attention in the water quality arena, a lot of bad attention. More importantly, a lot of good attention with recent initiatives to help improve water quality, address some of the limiting factors in the lake. And so today I thought it'd be helpful to talk through some of the water quality goals that we manage for Utah Lake, talk about some of the limitations in water quality, some of the conditions that we see, go through a brief history of Utah Lake water quality conditions, and then make that connection to stormwater like we're talking about here. And then for the next session, next week, we'll step into some more local watershed-oriented stormwater conditions, look at some local water quality projects, and some things that are being done to tackle the stormwater side of the equation. Okay. So water quality goals in Utah Lake, the state of Utah basically manages the lake for 3 separate goals, and those are aquatic life, recreation, and agricultural water. And we'll get into a little bit more detail on each one of these in the coming slides. But these are our primary designated uses for the lake. But I also wanted to point out that, Utah Lake plays really an outsized role in downstream water quality conditions for the Jordan River and Great Salt Lake, meaning that our management actions in Utah Lake really have a direct effect on downstream water quality. So we're talking about Utah Lake water quality conditions. It's not just about, the surrounding watershed, Utah County, Utah Lake. It's really about the greater Salt Lake area and the Wasatch Front in general. For aquatic life use, we spent some time a few years ago. It's like I had apologies for that. A little bit of a lag time on my side here, but for aquatic life use, we spent some time with some Utah Lake stakeholders a couple years ago to really kind of unpack those generic aquatic life, recreation, and agricultural uses to see what they really meant for folks in Utah County. And for the aquatic life use, we know that Utah Lake is a vibrant sport fishery. And so there was an interest in developing water quality goals that would enhance the fishery and protect human consumption of sport fishes. But we also know that Utah Lake is home of the June sucker, which is endemic to Utah Lake. It's currently listed as threatened on the endangered species list. And so really important to protect for water quality conditions to support production of June sucker into the future. For recreation, Utah Lake is what we call a primary contact recreational water, meaning basically that there's just a high likelihood for recreationists to ingest water, making it important that we design water quality goals that are oriented around protecting human health. And then for agriculture, the water in Utah Lake itself is primarily used to support agricultural production of crops and livestock. So water quality goals here need to be oriented around, promoting healthy livestock, supporting crop production, making sure water quality doesn't inhibit production in any way, and then, protect for human health in the case where agricultural products are intended for human consumption. So livestock is one example of that, but even a better example is in some of those produce type crops that we can source directly from our area. Okay. And then getting at Utah Lake's conditions in general, this slide shows some, basically worst case scenario photos of what we see in Utah Lake around harmful algal blooms. A lot of our use limitations or water quality limitations for our uses are, related to harmful algal blooms and algal production in the lake. For recreation, that's harmful algal blooms directly. For aquatic life use, just the excess production of algae and growth in the water, changes in the food web structure, and then ammonia toxicity, pH, elevated phosphorus, and nutrient conditions. Those are all really important things that limit some of our water quality conditions in the lake. The exception here are E. coli and dissolved solids for the recreation and agricultural uses. Those are, those are slightly separate issues that we won't get into in too much detail today. We'll talk a little bit about E. coli in next week's session. But for now, I'd like to focus more on this idea of eutrophication, since it kind of is all-encompassing for most of those use limitations that we're talking about. And basically, eutrophication just generally means it's nutrient rich, or that there's excess production and growth that's occurring in the lake than we'd otherwise see. And so for Utah Lake, the primary driver of these conditions is really related to the delivery of excess nutrients from the watershed to our lake. And then once the nutrients are in the lake, they can stimulate excessive algal growth and then have a direct impact on our water quality management goals. Throw in our warm, calm summertime conditions. Elevated temperatures, just like when we're, managing our lawns. Warm temperatures mean nice, healthy lawn. Hot summer days and combination with excessive nutrients is really kind of a perfect storm for promoting excessive algal blooms. Not a lot that can be done for managing our climate, but it's an important factor knowing that moving forward, with knowledge of climate change, that this is be an ongoing concern and something to be looking for as we develop management objectives for the lake in the future. And then the third factor here is just the disturbance. And so, our ecosystem, the lake's ecosystem, is out of equilibrium due to several factors that we'll get into in a couple minutes. But when we combine that disturbance with our climate and with those excessive nutrients, that's really just a perfect condition for excessive harmful algal blooms that do have an impact on how we use the water and our ability to do so safely. Okay. So just a little bit on the history of Utah Lake's water quality condition. Utah State University several years ago, working with the Utah Lake Science Panel that I helped manage, conducted a sediment coring study to help reconstruct the history of the lake and see how it's changed over time. This helps us understand what the primary drivers are in the lake and with respect to water quality. And what they found here is that prior to European settlement in the 1890s or so, that we had limited disturbance in the lake, very low nutrient concentrations. We had benthic diatoms that covered most of the lake bottom that helped stabilize the sediments. So the lake was not as turbid as it is today. We had lots of aquatic vegetation growing in the shallow bays and in the shallow shoreline areas, and basically overall a healthy ecosystem structure. Moving from the 1890s to the 1950s, we experienced some significant disturbance that we're able to see in the record here. This is primarily due to the introduction of common carp to the lake. Carp were very effective at disturbing the lake bottom, uprooting the vegetation that helped stabilize the sediments in the lake as they were foraging for food. And so this disturbance kind of basically reorganized the ecosystem, resulting in an increased turbidity and then setting the stage for further water quality impacts into the future from there. And so then as we move from the 1950s to the present, this coring study showed that, around 1950s is when we've really started to see dramatic increases in nutrient concentrations that were resulting from our changes in land use management practices, around the lake, and also rapid population growth. And then also around the 1950s, we were able to look at preserved alkyl pigments in the sediments. And we start to see a pretty significant increase in those pigments that were preserved, indicating that we had increased production of algae and cyanobacteria, harmful algal blooms, as we move from the 1950s to the 2020s. And then, the last factor here that's contributing to all of this, and is a primary driver here, is our rapid population growth. Between 1950s and 2020, Utah County's population went from about 82,000 to 660,000 people, contributing significant stress to the lake, adding more nutrients to the lake. And is one of those factors that will be probably a big stepping stone for lake managers moving forward to address and help manage water quality limitations that we would expect to see from continued population growth in the valley. But not all is lost for Utah Lake. There's a lot of initiatives ongoing currently to address water quality conditions in the lake. Several related to ecosystem recovery. We have ongoing carp removal through the June Sucker Recovery Implementation Program and its partners. There's several partners with the Utah Lake Authority and Forestry Fire State Lands working on reestablishment of aquatic vegetation, management of invasive vegetation. All of those things will help improve the ecosystem structure. And then we're seeing significant investments in the water quality arena through non-point source improvement projects, significant investments in wastewater treatment, and then lots and lots of stuff going on with the stormwater in the stormwater area that we'll be talking about. Okay. So first step really in improving water quality on the water quality side of the equation, I guess, is to really figure out where those sources of nutrients are coming from to the lake from the watershed. And so we've done some source investigations. It's rather complex. It comes from a variety of areas. We have municipal and industrial point sources, runoff from agricultural areas, grazing lands, atmospheric deposition, failing septic tanks. The list kind of goes on and on here. And so we're continuing to develop information on where these sources are specifically and how we might address them. And stormwater, as Kelsey was mentioning a couple minutes ago, we have lots of different stormwater connections to the lake. We have runoff from pervious surfaces, irrigation overspray, illicit dumping, construction site runoff, and others. And so during the next session, we hope to take a little bit deeper dive, get into some specific scenarios here, some specific projects in Utah Lake watershed in the communities, and just kind of understand what's being done to address some of these. And with that, I think I'll wrap up my presentation and hand it off.
Awesome, thanks, Scott. As Scott mentioned, and building off of Kelsey's information, we're sort of building an understanding of stormwater, what it is generally, and then to Scott's point about how it affects us at a watershed scale in Utah County. And now we'll turn the time over to Aaron Anderson Wentz, who is with Bar Engineering, to talk a little bit about some of the work they're doing to help manage stormwater.
Hey, thank you. Screen here. Okay, does that look right?
Try to switch your screens, Aaron. Up in the display settings, do the...
Yeah, we're seeing your notes.
Okay, there we go. How's that?
Perfect, thanks.
Okay, great. Hi, everybody. My name is Aaron Anderson Wentz, and I'm with Bar Engineering Company. I'm actually speaking to you today from Minneapolis, Minnesota. But I do a fair bit of work with our Salt Lake City office and have spent a career in low impact development and stormwater management. So kind of the anchor person on the triad of presenters today. And I'm going to talk to you about what low impact development is, give you some definitions, and then also talk about some case studies, kind of a light touch on that. But what I'm hoping is that by the end of this presentation, you have a sense for what low impact development is and how it might relate to the work that you do with your businesses or within your cities. And I want to make sure that I mention some of the examples I'm going to be presenting today are actually some of the good work done by folks in Spanish Fork. And James Darling is on the call here as well and can be a part of answering some questions at the end of the presentations if you have any specific for him about his experience with low impact development in his community. So wanted to make sure of that. Okay, so first off, just a general definition about what low impact development is. So as you've heard from our other two presenters, the way that we develop on the land can affect stormwater runoff. And so what you're seeing here is that this is a flow versus time chart is called a hydrograph. And what I'm showing here is sort of an example, hypothetical stormwater runoff hydrograph, flow on the y-axis and time on the x-axis under native non-developed site conditions. So if you had land use that looked something like what you see in the left photo over here, that you'd have flow over time that is relatively flat, kind of a slow progression of stormwater running over a watershed. And in those conditions, you have low flow rates coming off those pieces of land. And you also have little, relatively small amounts of runoff volume leaving because there's so much time for things to infiltrate and percolate down to groundwater. What happens when we develop our land? So now we've got a shopping mall on a piece of property and lots of impervious surfaces. And so under developed conditions, that hydrograph changes. And you can see there's a swift peak to that flow, and then it comes down over time. So it's pretty different than what we see under undeveloped conditions. And also in that kind of runoff under developed conditions, we have more volume leaving the site as well. And you can see that in the difference between the curves. So that red line compared to the yellow line, that red area represents extra runoff volume that gets delivered downstream. So in developed conditions, we have water running out faster and in more volume downstream. And that has an impact on downstream water bodies. I don't need to spend a lot of time on this because other presenters touched on this really nicely. There are many impacts of stormwater runoff on downstream water bodies. So there's things like flooding, but also lots of water quality implications, such as stream bank erosion that carries sediments and nutrients to downstream lakes and rivers, pollutants that get carried, which result in algal blooms. There's also a lot of loss of groundwater recharge when we're paving over large sections of land in our watersheds, and that has implications to downstream water bodies as well. So I wanted to introduce you to the concept of a first flush. I don't know if any of you have heard this concept before, but it's an important term in stormwater that is relevant to our discussion about low impact development today. So stormwater's first flush is the initial portion of stormwater runoff from a rainfall event that typically contains a higher concentration of pollutants than subsequent runoff. And this matters because understanding and addressing the first flush is really important for urban stormwater management because it can significantly impact water quality in receiving streams and rivers. And the pollutants in this first flush are things like sediments, nutrients, organic matter, heavy metals, pathogens, and other contaminants that have accumulated on urban surfaces during dry periods. So when we're talking about the best way to make a water quality improvement to downstream water bodies through development practices up in a watershed, we talk about capturing that first flush because that's the dirtiest bit of runoff that's going to come off a site. So we're not worried about all the stormwater that might run off a site. We're really mostly worried about the first bit, the first fraction of an inch. So in Utah, for new development and redevelopment greater than 1 acre or less than an acre, but part of a common plan of development, Utah has a MS4 permit requirements that state that they're required, Utah's MS4 permits require retention of the volume associated with the 80th percentile storm event which is about a half an inch, depending on where you are in the state, using low impact development practices wherever possible. And that is because that's really what they've defined as that first flush event. If you go to different parts of the country, that's going to be a different depth. You know, the first flush is not the same across the country. It depends on your climate and where you are. But for Utah, again, depending on where you are in the state, it's about the first half inch of water that the state is wanting folks to capture and retain and infiltrate if possible. So I'm going to talk to you about what that can look like on a site. So really, this is about mimicking natural hydrology through volume control. So infiltration is the most common approach. You know, if we have paved surfaces around, we can't get that natural infiltration anymore. There's ways that you can engineer and design ways for impervious surfaces to drain to pervious spots that are designed to promote infiltration. So these are things like infiltration basins, rain gardens, bioretention basins, underground infiltration, and tree trenches. And I'm going to show you some examples of what these things look like today. Over here on the right, this image that you see here from the Green Line Green Infrastructure Project in St. Paul, Minnesota, is an example of like a tree trench or bioretention swale that is meant to infiltrate. You can see water's coming in off the pavement, getting down through those plantings, and then down and away into the ground. There are other volume control methods that you can consider using, such as pervious pavements, green roofs, stormwater reuse, and even just planting more trees to have, frankly, just interception on leaves. That can be a very significant interception of water. So I just wanted to show you some pictures of what these can look like. This is an example from Minnesota. We're not going to talk about many Minnesota examples today, but I point this one out because it was one of the first residential rain garden projects in the country. This is from a suburb outside of the Twin Cities metro area in a city called Burnsville. And actually, if you're ever at a conference and you see a picture of a rain garden with a blue house behind it, it's this project. This one gets pictured a lot. So now you know. But these rain gardens were designed in a residential area to capture water running off the street. You can see in the lower left corner here, water comes down into this depressed planted area, and then the roots from the plantings help facilitate infiltration into the groundwater. And what was really cool about this project is that they did some monitoring. So they had a control neighborhood and one without rain gardens, and then a neighborhood with rain gardens. And they monitored the runoff before and after construction in both of these areas to see whether the rain gardens were making an impact. So the chart on the upper left here shows pre-construction runoff in both the control, which is the blue line, and in the study rain garden intensive area in the red line. And you can see that before construction, they were relatively similar. The chart on the upper right shows post-construction runoff. And there you can see the blue line, which is, again, the control with no rain gardens, significantly more runoff than the study rain garden intensive neighborhood in red. And so this was pretty good evidence for folks in this city and subsequent cities that rain gardens were a nice way of taking the edge off of stormwater runoff. This is an example of what one of these projects can look like in Utah. This is a Spanish Fork project showing a rain garden basin that's kind of along a road. So it's a linear rain garden. You can see the curb cut that we're looking at straight on there. And then there's a dry planting area with some rocks and some real drought tolerant species to add some aesthetic interest to the basin there. I'm going to show you some examples of underground infiltration. What's really nice about this option is that you can stack functions. So land is usually, you know, at a premium and finite. And so whenever we can stack functions and get multiple uses, in addition to low impact development or infiltration, volume reduction, it's a really beneficial thing. So here's some examples. First of all, just a practical note, these are the kinds of underground structures that you can put in place to help facilitate infiltration. There's just a list here on the side. Going from upper left, that's an R-tank stormwater module. It's like a plastic cage essentially that you can put underground just to make space to intercept water and allow it to have time to infiltrate into the soils below. Storm bricks are shown in the lower left. Those can go under roadways, so they can take a little bit more load and traffic. So if you can direct water under your road and get it into these chambers, it can allow it time to infiltrate. Storm tech chambers are great for larger installations. I've seen these used in like stadiums or, large big box stores. You can put these under a parking lot and have water infiltrating inside those chambers. And then the lower right is an option called storm filter. This is if you don't have the option to infiltrate. These cartridges have filtration media in them that can reduce pollutants. So we're not going to talk a lot about filtration today, but I did want to point out that sometimes you can't infiltrate. And when that's the case, you can use filters. Contech is another company that has a billion different options for different types of structures that you can incorporate into a design to get water underground. This is another example from Spanish Fork. So this is where they took those RTech boxes. You can't really see them, but they're in that left photo. They're down in that narrow strip. They're stacked too high. And then they put rocks on top of that and then plantings on the top. And so you might never know driving past this, that this is actually an infiltration feature. So water comes in a curb cut, filters down through the rocks, gets into those plastic cages that I showed you before, and then infiltrates over time. And they've had a lot of success with these in their city. Another example, so these are those bricks features underneath this black, you can see the fabric wrapped on the top here on the left. There's on the lower right, you can see the bricks canister, I can't remember what they're called, bricks, storm bricks, there we go. Storm bricks underneath there. So water's coming in off of an impervious parking lot, getting underground, and then infiltrating. And cars and trucks can drive over this stuff, no problem. I mentioned filtration options. My picture on the left here is just a reminder that you can also fabricate your own versions of filters. This is a rain garden filter that has a sand trench in the middle because infiltration wasn't an option in some really tight soils. Again, land is usually at a premium and finite, and so it's nice to consider adjustable parts and some flexibility. This is a project where there wasn't a lot of space for a large bank of underground chambers, but they were trying to infiltrate a lot of water. And so this feature has a small underground chamber that's installed underneath a shallow rock basin. So it infiltrates into the ground, and if it ever becomes overfilled, it can be drained out using a water main gate at an allowed rate. So in these kinds of projects, whether it's new development or retrofit, it's nice to include some parts that you can manipulate later if you want more or less flow, and also to help you facilitate some maintenance. So I like this example because it was a clever use of some moving parts. So here you can see the underground storage, the storm tech chamber underground, and then the shallow basin above, and then the water main gate there is called out that can be opened and closed to allow more or less flow in or out. Nice to design for some flexibility once you put things online. I also wanted to mention that low impact development design involves just making development plans, development designs that include less impervious surface in the first place. So this can be facilitated through narrowing roads over what you would typically do. There are ways to still have ample space for emergency vehicles, for parking, for traffic, but to narrow things up a little bit to allow for more green space on either side of your roadway, to allow for sidewalks, and also to allow some space for some rain gardens. And so this is an example of what that can look like. The existing section is on the top here, showing no infiltration features, no sidewalks. The proposed section is below, and there you can see there's boulevard rain gardens on either side of the roadway, a narrowed roadway, and then sidewalk on one of the sides. This is an example of a project that leveraged that. We often call these living streets because they allow for, again, this concept of stacked functions that make for maybe a more pedestrian-friendly section and a more aesthetically pleasing section for the people that are walking through it, while also including stormwater treatment. This is an example of some things that Spanish Fork is doing along these lines. So they're using some grass swales. You can see that pictured on the right, and then also in the cross-section below, they have these infiltration bays on either side, including some xeriscape planters, and they're narrowing up their roadways while still passing traffic. appropriately. And this is just another example of designing for less impervious surface. This is an example of a designed intersection in Spanish Fork where they've narrowed the necks of the roadways coming into that intersection a little bit. This has the benefit of slowing traffic as well, which is another positive effect of designing with this type of impervious surface reduction in mind. So I will tell you, sometimes low impact development isn't an option or can be especially challenging. If you have high groundwater, if you have high bedrock, contaminated soils, or compacted or silty clay soils. However, in those last two examples, you can consider filtration instead of infiltration. And I gave you some examples of how you might think about that. But the bottom line is that good design that minimizes the creation of impervious surface in the first place is always a good option and can also help you save money, can reduce the amount of stormwater you need to retain, and can also reduce your maintenance burden. So with that, I have a slide here on operations and maintenance. I think we'll need to leave that for a different day. So I think I'm going to jump off to the end here. And I just want to remind folks that for guidance around different types of low impact development practices, for ideas on how to design them, you do have a really great reference in your state, a guide to low impact development within Utah. That was put together for the Utah Department of Environmental Quality, Division of Water Quality several years ago. And this, along with many other resources, are available on the DWQ's website. So with that, I will hand it back to Jake.